We learned about word2vec already, but there are plenty of other ways to compute word embeddings as well. In this video, I'll discuss two other popular word embedding techniques, fast text and glove. I'll talk about each technique individually as well as compared with word2vec. Fast text is an extension of word2vec that also incorporates subword models. Because of this, it's better able to handle unknown words or to deal with sparse training data. A subword is exactly what it sounds like, part of a word. So in fast text, each word is represented as itself along with a bag of its constituent n-grams. A skipgram embedding, just like what's used in word2vec, is learned for each of those constituent n-grams as well as the full word. Then, those embeddings are all summed to form the final word representation. Since these learned word embeddings are based not only on the full word, but also on smaller parts of it, this means that when unknown words are encountered at test time, the model can still produce representations based on the word's constituent n-grams, which are much more likely to have been encountered previously. So now we've seen a few ways to learn word embeddings, and word2vec and fast text are very similar to one another. Fast text is basically just word2vec plus subwords. Word2vec and fast text are both predictive word embedding models, which means that they learn to predict whether words belong in a target word's context, and in doing so, they end up producing word embeddings. Not all word embedding models are predictive. Some are count-based instead, making use of co-occurrence matrices like the earlier bag of words models we saw. Glove is a word embedding model that combines aspects of both the predictive and count-based paradigms. The reason why glove embeddings combine aspects of predictive models with the count-based paradigm is that with count-based models, co-occurrence matrices can quickly grow extremely large. We can easily envision that based on the samples we've seen, if we take a large text corpus, like all of Wikipedia or something like that, we would need to create an n by n dimensional vector where n is equivalent to the vocabulary size of all of Wikipedia. That's simply not scalable. An intuitive solution to increase scalability would be to perform dimensionality reduction on our very high dimensional representations, but given their size, even typical dimensionality reduction strategies may result in too much computational overhead. Instead, Glove learns to predict weights in a lower dimensional space, and those weights correspond to the co-occurrence probabilities between words. This means that while glove models are more efficient than a pure count-based model, they still retain some of their advantages in terms of interpretability, which is nice because that allows us to more easily figure out why models trained on these representations are making the decisions that they're making. Since glove models encode the ratios of co-occurrence probabilities between words, that also makes the resulting representations inherently well-suited for things like word analogy tasks. We can walk through how glove works here. First, we start out by just building a huge word context co-occurrence matrix. From there, we then establish the equation here, where we're defining soft constraints for each word pair. And basically, we want to learn weights for vectors t sub I and c sub j, plus a bias term b sub I and a bias term b sub j, such that these elements combined, as shown in the equation, are equivalent to the log of the co-occurrence count for t sub I and c sub j. Then, we define a cost function, making use of the equation we just saw, along with a weight function. The goal then is to minimize that cost function in order to learn optimal values for w sub I and w sub j. Those embeddings are then the learned representations that we make use of in our downstream tasks. Basically, this means that glove is just a log bilinear model with a weighted least squares objective. It works because the ratios of co-occurrence probabilities that it learns along the way are useful for encoding word similarities and differences, and these similarities and differences are, in turn, useful components of meaning. The fact that glove is fundamentally based on encoded similarities and differences is also why the representations are so well suited for analogy tasks. So now we've covered a nice variety of foundational word embedding techniques. The two you'll encounter most when reading papers from the last 5 years or so are word2vec and glove, and the question of which of those techniques is better really depends on your data. In general, despite their different ways in getting there, Word2Vec and Glove tend to produce pretty similar word embeddings. Word2Vec is slower to train but less memory intensive, whereas Glove is faster to train but more memory intensive. So speed versus memory may be another trade-off to consider when deciding which representations to incorporate in your own application. An important thing to note is that every word embedding technique we've covered produces context-independent embeddings. That means that they're the same for a given word regardless of the context in which it occurs. Recently, there has also been significant work in NLP towards developing contextual word embeddings, which produce different representations for the same word in different contexts. We're not covering those in detail in this course, but popular recent techniques include Elmo and BERT. So don't be alarmed if you're reading an NLP paper and you suddenly feel like you're on Sesame Street. Those are just other word embedding techniques.